We're going to look in more detail at the first three wave functions, the first three radial wave functions for the hydrogen-like system. So we've got one electron, we've got one nucleus, it's got a charge, we've already scaled away the charge. So we're going to think in terms of characteristic distances, or if you want, just think in terms of hydrogen, and we'll think in terms of Bohr radii. So the first function we're going to think about is n equals 1. So for n equals 1, it's the 1s orbital, of course, and we're going to use this bracket notation, and we're going to specify the three quantum numbers, n, l, and m sub z, and n is 1, because that's the 1, and then l has to be less than n, so it's got to be 0, and poor old m sub z has to be less than the absolute value of m sub z has to be less than l, and l is 0, so it's 0. So we just got one state for n equals 1. And we call it 1s, of course, and the 1 is the 1. The 1 is the principal quantum number, and as you know, the s is a relationship that's actually specifying that quantum number L. And so s means that there's 0 angular momentum, SPDF, etc. is just a sequence that's a code to specify the angular momentum quantum number. So in this case, there's 0 total angular momentum, and so of course there's going to be 0 z component of the angular momentum as well. And now we've got our little axis here. We've got our A0, or R0, and a scaled radius of 1 there. And the function R of R is really simple. It's e to the minus rho. So it's just this purple exponential that we've already been talking about. So it's already got that exponential decay. It's pretty boring. The 1s orbital is pretty boring. But when we turn it into a probability distribution, of course, rho is equal to zr over A0. We turn it into a probability distribution. It's going to go like r squared times that capital R radial wave function squared. And as we already discussed, that has a pretty sharp maximum at roughly rho equals 1. For z equals 1, that's roughly 1 Bohr radius. The maximum is, in fact, at 1 Bohr radius. So the 1s orbital is confined to about a Bohr radius. Its radial function is pretty dull. There's no zero crossings. The maximum is at z equals 0 for the wave function, but since that is just one point, the probability of actually finding Clarissa at z equals 0, at rho equals 0, is basically nothing, because there's really no volume in space at that very specified point, and instead we find Clarissa out at some distance in general there. Not much to be had. And the angular part we're going to talk about in class more, but there's nothing to it. The 1s orbital has no angular momentum. There's no energy associated with angular motion, and so, not surprisingly, there's no variation in the 0 function either. It's just plain flat boring. There is curvature in the function in the r direction. It's an exponential. And so there is curvature, there is kinetic energy associated with radial motion, and so that's where the energy comes from. It's all in radial motion, and none of it is in angular motion at all. It's just a blobbed out function that can't be said to be rotating in any way, shape, or form. Now let's look at the n equals 2 case with 0 angular momentum again. So we're going to go 2, 0, 0. Now we don't have to be 0 in the principal quantum number L, but we're going to look at the case where L is equal to 0 first. I'm going to give myself a little more space. Actually, it's the same space. I've just labeled it. We're going to go out to about 8 Bohr radii here. And this is the 2s orbital. Again, n is equal to 2, and so that's the 2 there. And s is the code for the total angular momentum quantum number. And s is a 0 total angular momentum quantum number. So the radial function now looks like 2 minus rho, and we've got e to the rho minus rho over 2, because the n is now 2. And remember, since we're dividing by that 2, this is more permissive. We can move out farther. The 2 minus rho is the stuff part. That's the polynomial part of the function. And the polynomial is basically in charge of wiggling. It's in charge of going up and down and making nodes. And so we see 2 minus rho. That means we're going to have a node at 2 characteristic distances, or 2a naught in the case that we're drawing here, where z is equal to 1. So that's specified where the node is going to be, and I've circled it in red. So the function, the wave function r, which we're going to draw in purple, is going to look something like that. It's going to go through the node. The probability distribution is going to look like this. Okay? So the function, again, has a maximum at r equals 0. It goes through 0 at r equals 2 Bohr radii, if z is equal to 1, goes to a secondary, a minimum value, and then the exponential part tells it to get back to 0 eventually, and it does that in, at 6 or 7 or 8 Bohr radii, it eventually basically gets back to 0. If I take this thing and I square it, and I multiply by r squared, I wind up with this green curve here. So the green curve has a bump because there's purple, positive purple, in the sort of close to the nucleus, right? So there's a little bump there. But then at the 0 crossing, at the node, it has to go down to 0. It's got to look like a parabola at the 0 crossing, basically. And then it's going to go back up to another secondary maximum that turns out to be way out there at 4 or 5 Bohr radii, and finally comes back down. And it comes back down eventually because that exponential term is definitely going to win. And we're going to go to 0. But so the n equals 2 case with no total angular momentum, there's got to be one node. So we're going to the second we're going to the second energy level. We go from 0 total nodes in n equals 1, then we're going to have one total node in n equals 2. So the total number of nodes is going to be n minus 1. And that node, for the 2s case, when there's no angular momentum, there's no angular nodes, that node is left over and it's in the radial direction, and so there it is, circled in red. Now obviously we're going to look at the, there's our maximum and our secondary maximum. That secondary maximum is really, 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 really important, and it's going to come up a lot. But right now, for a single electron hydrogen atom, it actually doesn't matter very much, but it's going to matter a lot, little bit later on. So now let's look at the final wave function for this part of the conversation. We're going to look at the n equals 2, l equals 1 solution, and that's, of course, the 2p. So n is equal to 2, l is equal to 1. This is 2, 1, and we can have 3 different values of m sub z here. We can have 1, 0, or plus 1, negative 1, 0, or plus 1 for the m sub z value, and this is the 2p orbital. Again, the 2 is the 2, and the p is now telling us that the total angular momentum quantum number is 1. I should have that negative 1, 0, and plus 1 inside parentheses, I think, because there's just 3 quantum numbers that I specify for any given value of this. So the actual radial wave function now goes like rho, and it's also got an e to the minus rho over 2. So you see something interesting happening here. The order, when we have n equals 2, the polynomial is going to have an order of n minus 1. So in this case, it's going to go like radius, like rho to the first power. So there's always going to be a 0 in there. It has to cross 0. But when I made the angular momentum quantum number not be 0, what I get is the 0 value of that function is at r equals 0. And because r can't go less than 0, it doesn't actually cross 0, it just touches 0. So the radial function now has a 0, not a node, but a 0. It's not a 0 crossing at r equals 0. And then the exponential does its thing. So that's kind of interesting, and there's a lot of reasons for it. But the reason is that we've got angular momentum. So if I have angular momentum, I've got L is equal to 1 after all. Clarissa cannot get to the nucleus with angular momentum. Any amount of angular momentum, and you just can't do it because your radius goes to 0, and that's impossible. So the angular momentum excludes Clarissa strictly from actually getting to r equals 0, which is pretty frustrating because that's where Clarissa really wants to be, but such is life. So that charge cannot get exactly on top of the nuclear charge because of the angular momentum. So then the wave function looks like this. It actually goes up to a maximum and then goes back down. That's the wave function itself. So it goes up linearly at small r and then gets shoved back down. And then we do the probability distribution, and it has this kind of shape here, and it's got an actual maximum in the probability distribution out there in a roughly, let's say, 4 and change Bohr radii. So that's the maximum probability of finding the 2p electron out there as well. And you notice the 2s and the 2p orbitals actually have very similar locations for their maximum. So you tend to find the electron in the same general area. It's actually true that the 2p is the maximum probability is actually somewhat closer to the nucleus than the 2s. The 2s is somewhat more extended. But the thing that the 2s has that the 2p don't have is that secondary maximum. So that secondary maximum is present in the 2s because it doesn't have any angular momentum, and it's perfectly capable of getting close to the nucleus. In fact, the single most likely place to find Clarissa in a 2s state is right on top of the nucleus. It's just, again, that that's not a very common piece of real estate, and so overall it's not very probable. Whereas once I give Clarissa some angular momentum in the 2p orbital, there's no way I can find the Clarissa anywhere near the nucleus. So the probability of finding the electron exactly at r equals 0 is 0, strictly. It won't be there at all. And so then when we get to the probability distribution of radius, p of r, there's no way at all. It's absolutely strictly excluded from being around the nucleus. And that secondary maximum and the strict exclusion of the electron from being in the vicinity of the nucleus as we add angular momentum is a critical feature of the way these wave functions play out. But I must stress that for the single electron solution, the hydrogen-like system, which is all we're talking about here, where these wave functions are exact. So we know these wave functions precisely for this problem. The 2s and the 2p orbitals have exactly the same energy. It's negative z squared times the Rydberg constant for hydrogen times 1 over n squared, or 1 over 4. In other words, for z equals 1, the hydrogen system, in the n equals 2 case, it's about negative 27,000 wave numbers. Precisely the same number for the 2s and the 2p. So there's no difference at all in the energy level if I just have one electron. Multiple electrons we'll get to later, that's going to make a difference. But for one electron, the energy is exactly the same. But the structure of the radial distribution will be critically important when we start adding extra electrons to the problem.